Okay, everybody, welcome to the fifth lecture in ECE 576, ECE 560, which is modern control theory. So before we get started, does anybody have any questions regarding previous material, homeworks, or quiz? You can also write it in the Zoom chat if I am not able to hear you. Okay, so last lecture we've been looking at controllability of systems. We saw the controller canonical form and how do we convert to it, and what's the similarity transformation that leads to the controller canonical form from any system which is expressed in a state space representation. So a quick remark before we move on from the controllability determination. And today we are going to move more towards controller design, and from there we will see another property called the observability, and you will see why that is important in this context here. So the remark from last time basically just says that controller canonical forms can be there could be many different controller canonical forms. Just as we said that state space representations are not unique, you can have infinitely many state space representations. So you can also have many different controller canonical forms. So different books use different conventions. The one that I showed you is the one where the last row contains the coefficients of the characteristic polynomial of A in the extremely last row, and with the reverse order and negative signs. So we'll see how and why these are different. So based on the conventions used. Okay, so let's do a quick proof to see why this is even possible. So assume that a system is already in a controller canonical form. We can actually transform it into a new system. And one simple transformation can be using an exchange matrix where the rows can be exchanged. So if it's in a controller canonical form already, then we can transform it again using a permutation matrix. That exchanges rows or columns. So one example of a permutation matrix is the exchange matrix. So let's say that there's a matrix E, which transforms the original state space X into a new state space X bar. And let's say this is the exchange matrix. When I say exchange matrix, I really mean that it's zeros all one here, all ones here, and the rest are all zeros. And so the the diagonal. It's kind of a it's like an identity matrix, but the this diagonal here is all one. Okay, so for example, if we had this scenario, then you know your A bar will be T times A times T inverse, but here we have E as the transformation matrix. So we'll have E times A times E inverse, and we will have B bar will be an E times B. Right, so what is essentially happening is you will have here a different order of rows, right? So different order of rows and columns. So and the same thing here with the B. B bar will have a different order of rows from the original B. So in our previous lecture, we've used the convention where the last row. So let me just fix this quickly. So we've used the convention where we said the last row has elements of the characteristic polynomial. The convention used in this is that A bar is, you remember or recall from the previous material, we had all ones here and zeros everywhere else. And the last row is actually going to be minus A0, minus A1, all the way up to minus AN minus 1. Okay, and a B bar turns out to be zeros all the way, and the last element is 1. And your C bar is going to be B0, B1, and all the way up to Bn minus 1. Right, and where A0, A1 till An minus 1 are coefficients of the it's the denominator polynomial, and people also call it the characteristic polynomial in the transfer function. You can always go back and look at the previous lecture to see what was the exact polynomial and how these coefficients came here, right? And the B0, B1, all the way to Bn minus 1, they are coefficients of the numerator polynomial. Okay, numerator polynomial in the transfer function. So so we saw this a canonical form, and from our discussion right now, if you use any order of this form, meaning you exchange the rows or columns, that is also a canonical form, right? But we are using this particular notation because it's consistent with our book. But obviously, when you read literature, you will find many different canonical forms. So it's natural to ask yourself why we need a canonical form, right? What is so special about this? And probably I already mentioned earlier, but let me reiterate the idea here. So why do we need a canonical form? After all, it's the same system. So same LTI system, but we have a different form for it. So the idea behind is that if you want to change the system behavior, you would only need to change one row in the matrix. So instead of determining every element of the matrix A, you will only be determining one row of the matrix. So as long as you change that row, your matrix behavior can change, or the system behavior can change. So let me write it more formally here. So if we have to change the system behavior, we would need to change simply a single row. Just one row of the matrix A. In a canonical form. So again, the idea is you have a system which is defined by x dot equals to ax plus bu. Your system behavior is determined by the eigenvalues or poles of the matrix A. And now when you want to control the system, you actually just want to change the system behavior. So if the system is expressed in the canonical form, it becomes easier because you only have to exert control over these coefficients A0, A1, and so on, right? So there has to be a way to do the modification, and we do it in a systematic way. You will see as we proceed in today's lecture, what is the idea behind controller design, and particularly a feedback controller. Okay, so let's also clarify a few more ideas before we go to the new content. So last time we saw controllability in detail. We saw the method, how to prove if a system is controllable or not, and we also did a decomposition of the system into controllable and uncontrollable subsystems, right? So if you were given an original system, not all of that may be fully controllable, but parts of it might be. So we saw a decomposition of the system into two parts. So when we say controllability, we oftentimes mean that the system is completely controllable, right? So just as a disclaimer here, I want to mention that controllability will refer to the complete controllability, right? Meaning that all the states are controllable. Or complete, let's say, complete controllability. And just to reiterate, when we say complete controllability, we are saying that we have the ability to go from any state to any other state, right? So to go from any initial state to any final state which we already said this last time, but xt0 is x, which can be anything in Rn, and so there exists a u over time that will result in an x at t1, which is equals to x1, and that also belongs to Rn. So you can actually map from any initial state to any final state with a reasonable control input u. Okay, and the next fact is that there are weaker forms of controllability. Right, and let's see what are these weaker what are the weaker forms? So the first weaker form is called a reachability. Okay, so what does that mean? It means that even though you're not able to steer the system from any initial state to any final state, you are in some way only confined to a certain subspace. Right, so that means there are some restrictions on where system states can be steered. So it's only confined to a certain subspace. Right, so in other words, an input u of t can only steer the system to a set of possible states. So you cannot reach every state, but there's a set of states that you can reach. So that's the idea behind the reachability. There's also another weaker form of controllability that's called controllability to the origin. So that means wherever the system is, you can always bring it back to the origin. Right, so it is better than having completely uncontrollable system, but what we want to say here is that the system can still be brought back to the zero state. So if the system can be steered to the zero state in finite time. Right. So for example, if you're driving a car, obviously you cannot make the car fly into the air, but you can always bring it to a stop using your brakes. So there is not complete controllability, but there is controllability to the origin at least. That's one weaker form of controllability. Now, the question is, what are the options if the system is not completely controllable? Right, so that will bring us to our idea of feedback control systems. So what if the system is not completely controllable? Okay, so last time we saw one possibility. So we can actually decompose it into two parts. So first, what you can do is we can decompose it into controllable and uncontrollable parts. So what that means is, let's say there was a system and you figured out using the controllability test that it's not controllable, which in other words, it means that the controllability matrix of that system is not full rank. So then what you can do is you can break it down. And that means there will be two subsystems, right? One is the a controllable part, and the other is the uncontrollable part. Okay, so controllable part means there is a XC dot, which is AC, A controllable, X controllable, plus B controllable U, right? So that's the dynamics of the controllable part of the system. And there's also an uncontrollable part, which is XC bar dot is equals to A uncontrollable, X controllable, X uncontrollable. And there is no U here. There is no second term here because it's not controllable, right? And we already saw this last lecture that a decomposition can be done if the system is not controllable. Okay, so we had these two systems. One has an input U, the other has no input, right? And then the outputs can actually be combined here to give you the final output Y, right? So our original system, you can actually write it as a decomposed form where one of the subsystems is being affected by the input. Here, you know, the input U does not affect this part. Okay, so great. First thing we did is we decomposed the system into a controllable and uncontrollable part. And then the next thing we have to do is we have to make sure that uncontrollable part is stable. So we have two subsystems, and one of them there is an input U, the other is not affected by any input. So we have to make sure that the uncontrollable part is stable. And if that's the case, then we say that the system is stabilizable, right? Then the system is considered. So if you ask me about the stability of the system, I will tell you the system is unstable, but it can be stabilizable, which means that the uncontrollable modes or uncontrollable parts are actually stable. So it's considered to be stabilizable. Okay, so for example, I will take the previous example, previous lecture. There was a controllability, controllable decomposition. You can always go back and see that example. So if you take that example here, you will see that the A bar was actually 0, -2, 1, -3, 1, 0, 0, 0 here. Oops. It was 1, 0, and -3. Okay, and the B bar was actually 1, 0, and 0. So, so essentially, this part is the controllable, right? A bar controllable. This piece here was the A bar uncontrollable, and this is just A bar 1, 2. This piece here is the B controllable, and this last element is the B uncontrollable. Okay, so this was a decomposition of the original system, and in this case, I actually told you last time that X3 is uncontrollable, but luckily, you know, the matrix A that governs the uncontrollable part is -3. So the eigenvalue is again -3, and therefore the uncontrollable part is stable. Right, so let me write down this case here. So in this case, X3 is uncontrollable. Okay, but luckily, the A bar uncontrollable is -3. So the eigenvalue you know, which happens to be -3 as well, right? So eigenvalue of a number is the number itself. Which happens so the eigenvalue is negative, right? Which in other words lies in the left half plane. Okay, so that if that's the case, then the uncontrollable part is stable. Okay, so overall system is stabilizable. So I want everybody to understand that from this example, basically when we did the decomposition, the rank of the controllability matrix was 2. So that told us that there are 2 states which are controllable, and the third state is uncontrollable. Okay, and when we got that information, we saw that the decomposition actually can be split up like this. So 2 of them will be you know, we'll have a 2x2 controllable part, and the rest will be uncontrollable part. This is where we drew the line. And once we draw the line, we will check the stability of the individual parts. So stability we will check by using eigenvalues, and eigenvalues of the controllable part are different. Eigenvalues of the uncontrollable part are different. And we just have to make sure that the uncontrollable part has all eigenvalues in the left half plane. If that is stable, then we can take care of the controllable part by using the control input. Okay, so so we have seen that systems can be taken care of if their uncontrollable parts are stable. So what next? Question is, if the system is controllable, what can we do next, right? That's the thing that we've been talking about since the first lecture. So if the system is controllable, then we basically design a controller, and controllers usually we saw that open loop control is not that great. So we want to design a feedback controller. So we can actually design a feedback controller that can achieve certain desired functions. So what are those functions that a feedback controller can be designed for? So I'll mention here just three. So first thing is to track a reference state. So for example, if you recall your first homework, there's a cruise control example. So in a cruise control, basically you have a reference speed to reach to. So one of the goals of the feedback control is to track that reference state. So from anywhere to anywhere, the controller can actually lead you to the reference state. Okay, so in a cruise control, basically you want to reach a target speed. So that is your reference there. The second thing is, or second possible objective of a feedback controller could be disturbance rejection. So what that means is, for example, in your cruise control, if there is a hill, then your car starts to slow down. So in that case, you want to maintain your speed. So the controller will perform that type of function. Right? So the feedback controller will actually try to, so for example, in a cruise control example, if you try to maintain the same speed uphill, that's actually a disturbance rejection, right? In other words, you are trying to compensate the effect of external conditions. Right? If there is a disturbance from the environment that changes your state, the feedback controller can correct it. Right? So for example, if you try to rotate a dish antenna to a certain direction and the wind kind of changes its position or orientation, the feedback controller can actually realign it by adjusting and compensating for the disturbance that was caused. So these are two primary objectives, but there's a third one that's actually to meet performance specifications. Right, so you may have applications where a certain performance specifications are there. For example, how quickly the system respond, and what is the rise time, what is the overshoot, etc. So when you look at your seat adjustments in a vehicle, when you press the button, the seat starts to respond. So how quickly that responds can be designed by a controller, right? So you may have some performance specifications that you want to meet. So that's where a feedback controller will actually help you. So it could be rise time, or it could be an overshoot, right? And so on. So these type of things can happen, and feedback controllers usually help you meet these performance specifications. So when I say you change the behavior of the system, it's really about changing the position of the poles in the system. Imagine that this is the pole 0 plot, and this is real and imaginary axis. Consider that these were the poles. A feedback controller can actually change the position. Right? So, I mean, here it is in the unstable region, but you could always bring it here, right? Meaning you can bring it here, right, with feedback control. Or there's also a possibility where you can, place it anywhere. So you could place it them here. For example, this one you place here, and this one you place here. Right? So that's according to your design specifications. So remember, if you place the poles here, your response will be, it will have some oscillations, and it will kind of reach a certain state, right? Could be 0 state or whatever state. But if your poles are in conjugate pairs, you will have this type of behavior. Let me draw it again. So let's say let's use a black color here, right? So you will have a system behavior which is kind of this, right, over time. But if you have if poles are in complex conjugate, and remember, if the poles are on the real line, then you will have a response like this. Okay, so so that's the 3 possible objectives of a feedback controller. And now the next stage is, how do we design a control input, right? We continue to mention that we want a feedback controller, what it can do, what's the objectives, but now is the time where we can talk about how to design the control input. The control input in a feedback controller. Okay, and the answer to this is using the state information. So if you know what the state of the system is at every time, then you can use the state information in the input. And one example is the linear state feedback controller. So when I say linear state feedback controller, I really mean to say that your input u is some linear function of the state. So linear function can be, for example, negative kx. It's a linear function of the state variable, right? So k is a vector, x is a state vector. So x is, remember, x1 all the way to xn is a vector of states, and the vector k is a row vector k1, k2, all the way to kn. So if you have that type of input, then that's a linear state feedback controller. So in other words, your u will be minus k1 x1 minus k2 x2, and then all the way to minus kn xn. So so if that's the controller, then objective here is to find the k's. So objective is to find the k, k1, k2, kn that achieve the desired objectives. Right? Whether it is tracking a reference, whether it is disturbance rejection, or it's meeting performance specifications, the question is how do you decide what the k values are? So system behavior or objectives. So I mean, that sounds like a good strategy, but unfortunately there is a small caveat here, and that caveat is that this controller is not implementable. So unfortunately, the primary reason for not being implementable is the fact that the state information is not available. Right. So why? Because because complete state information may not be available. Right. So that means, for example, if you have a system which is running according to certain dynamical behavior, you may not be able to see it all the time. You may not know exact state of the system at all times. I mean, there are cases where you can do it, but that's not the general case. So in other words, if there's a system with the input u, it's kind of a it can sometimes be a kind of a black box where you know the input, you know the outputs, but you cannot know the internal state of the system. For example, can be imagine there's a vehicle which you know the dynamics of the vehicle, but let's say it goes under the tunnel. And then that's where you don't know where the car exactly is at a certain time, but you know the dynamics, right? So the exact state may not be visible. So you cannot assume that you know the state and that state information can be directly fed back into the input, right? So there has to be some measurement device that kind of knows where the state is. And even if you know it, there may be inaccuracies, there may be delay in the input. So state feedback controller um, is not a viable option when it comes to designing a feedback controller. So imagine this is a black box. You only know A, B, C, D, but the state X at each time is not known. So we cannot use U is minus KX, right? So the reason why we cannot do this, again, if you want to look at it in another way, let's say there is a system with a certain input and a certain output, then what you're looking at is trying to do a U, which is, let's say there's an R here, and you're trying to actually get X out of here, multiplied by K, and feed it back to the original system, right? So the problem with this is not possible because internal state X cannot be determined in all cases, right? So then what do we do? Obviously, we want to do a state feedback controller. We want to take the state information, feed it back. So one possible way to avert this difficulty is we estimate the state from the output. So let me draw the other figure. So one possibility to avert or to avoid this difficulty is to estimate the state from the output Y. Okay, so in other words, let's say, again, we have the same system, which is a black box, but we have the output Y, and we can feed the input to the system. So what we do is we actually, from the output, we use an observer. Right, so observer is a system that can construct an X hat. Right, so it will give you an estimated state, internal state of the system, and with that X hat, you can actually use a K and feed it back to the system. Right, so if you have that, then you can actually track a certain reference signal. If the references are, then using an observer, you can actually estimate this internal state and then use a state feedback controller. So in other words, what I'm trying to say here is that you use an input which is minus k x hat, right? So this is possible. Where x hat is the estimate of the state x, and is asymptotically accurate, meaning that that hopefully the observer is able to construct the state very accurately, and if that's the case, then your feedback controller will perform in a well-defined way. So when I say asymptotically accurate, basically what I'm trying to say is that x hat at time t minus x of t, which is the kind of error here, or mean squared error, which is actually can be written as the sum of I equals to 1 to n small xi of t hat minus small xi of t whole squared, and this goes to 0 as t goes to infinity. So meaning that the mean squared error of the observations goes to 0 as the time goes to infinity. So as long as the observer has constructed a estimate of the state which is asymptotically accurate, you can use a feedback, linear state feedback controller, and that should do the trick. That should actually help you achieve the system design goals. Now, in order to be able to construct an estimate, the system has to be observable. So that's the new concept here of observability, meaning that you should be able to construct the state from looking at the output. So let me write it here. So to be able to construct an estimate of the internal state of the system, it must be observable.
Sorry, Professor.
Yes.
In this graph, US R minus KX hat or just minus X hat?
1 second. Yeah, so you're right. I mean, it should be R minus KX hat, but I'm just assuming reference is 0 here. So I mean, you can delete it, but in general, it should be R minus KX hat. And interesting.
Thank you. I understand.
So interestingly, for any system, you can actually assume reference is 0 because you can always transform the system and create that offset of R, right? So as long as you can go to 0, you can actually reach any state R or any reference R. But you're right, generally you should be R here, but assuming R to be 0. And majority of the course, we will assume to be 0.
Thank you for your explanation.
So we came to a new concept here about being observable. So let's look at what a observable system is. So we've been talking about controllability and being controllable. But now we are faced with the next challenge that the system has to be observable, right? And it's a similar, but in some sense, you have to so you have to use the output of the system to get to the state. So it's not only the matrices A and B, it's going to be a different set of matrices that's affecting the observability. So I'm going to write it more formally here, the definition. So an LTI system, let's say expressed in a state space form, is observable if for any unknown initial state x0, there exists a finite time time t such that the knowledge of the input of the input u and output y over the period 0 to t can uniquely determine. So this is important. So if you know the input, if you know the output over this period of or interval of 0 to t, you're able to uniquely determine what's the state of the system, or uniquely determine the initial state x0. Right? So otherwise the system is unobservable. So indirectly, what it means is you are not able to determine what the state of the system was at each time interval or each time instant, right? So I can draw a diagram here, meaning that if there is a x0 and there is a x at final time t, and you know what the input is in the interval 0 to t, and you know what the output is in 0 to t, then you can actually uniquely determine what the state was in the middle. Right? So you know the system dynamics, but you do not know the state. So can you actually go back and determine the state from knowing the input and the output? If that's the case, then the system is observable. Otherwise, system is unobservable. Now, how do we determine if a system is controllable or not? So that's related to the matrices A and C in an LTI system or a state space system. So observability is related to the matrices A and C in the state space model. Okay, well, so when I say x dot is ax, the bu and the y is cx plus du, then the a and the c are the ones that determine the observability. Okay, and the a and b are determine the controllability. So matrix D does not play any role in determining either controllability or observability. Okay, so when we want to do this, basically, just like the controllability style, we will construct a observability matrix. So the observability matrix, or let's say the observability of the system, in state space can be determined using an observability matrix. And an observability matrix has the general form O. So we represent it as O, A, and C. O is a function of A and C, and it can be written as an augmentation of the matrix or the row vector C, CA, CA squared, all the way up to C times A to the power n minus 1. Right, so analogous to the controllability, and I can mention here recall. If you remember the C, actually this controllability of A and B was the vector B and then AB, A squared B, A to the power n minus 1 times B, and then you determine the rank. So same thing here. This is the observability matrix. Oh. So if the observability matrix of A and C is full rank, right? Or in other words, if it is invertible, then the system is observable or completely observable. So the same idea, just like we did in a controllability case, if this observability matrix is full rank, then it means that the system is fully observable, meaning that all the states can be reconstructed if you know the input and the outputs of the system. Right, so the observer can be designed to give you the complete state information. So let's do a quick example to show how we can test the observability of a system. It's going to be similar to the previous controllability examples, but just for you to have a hands-on experience. So let's say a mechanical system is described by the following dynamical equations. So check if the system is observable. Okay, so I think this is an opportunity for everybody to do it with me and try to see whether you can figure that out. So the system is defined as x1 dot equals to x2. The x2 dot is equals to minus k over m x1. Actually, this is m1 and plus 1 over m1 u. Then we have x3 dot is actually equals to x4, and then x4 dot is equals to minus b over m2 x4. Right, and we are also given that y is equals to x1. Okay, so first step, I mean, obviously we want to go to an observability matrix, which was, remember, the augmentation of rows. We have to do C times A squared, and so on. So let's first figure out what is A and what is C. So this system here is actually in the form of differential equations. So we can convert it to state space by observation. So let's express it in a vector matrix form. So it's x1, x2 dot, x3 dot, and x4 dot. This can be written as a 4x4 matrix. So we have 0, 1, 0, 0. And then we have minus k over m1. We have all zeros. And then we have 0, 0, 0, 1. And finally 0, 0, 0 minus b over m2. Okay, and then for the u part, u only appears in the second state, so it's going to be I think I made a mistake, 1 over m1. So it's going to be 1 over m1 and u here, and x here. Let's write it more consistently. Instead of all of this, let's just say this x dot. Right, so this is x, and then we have a b and this and a u. And for the output, it's going to be written as a cx, and then there is no d here, so the c can be observed to be this vector. Okay, so this is the c, this is the b, and this is the a.
Professor, will D ever play a role in any of this?
Well, that's a good question. So in a lot of systems that we are looking at, the D is not playing a role, but our mathematics has to have that D. So the thing is that if you have this system, so basically, it's like you have a U here, and this U is actually going to, there's a D here, and then this is the Y, right? So it's like a part of the input appears at the output. So that's the purpose of the DU. But in a lot of systems that we're looking at, we are considering the fact that the input doesn't go directly at the output, right? So we will mostly see D being absent. But it's part of the calculus. So whenever there is, you can figure it out. But for controllability, observability doesn't matter, right? Because why would it matter if you want to observe the state? So state observation only requires A and the C. And same thing for controllability. If the input is reflected at the output, it doesn't say anything about whether it can control the state variables or not. So, but that's a good question. I mean, you should be careful that it's not like D doesn't have any role in the system, but it's like a feed forward kind of a gain, which a lot of the time doesn't really matter. So when we talk about feedback control systems, A, B, and C are the most important matrices.
Okay, thank you.
So, okay, we've converted it into the state space, and now we construct the observability matrix, which is the CA, right? So we have to go to up till n minus 1, and n here is 4, so we'll just have to go to CA squared, CA cubed. Okay. Now, so because these are large matrices, I'm not going to, but actually the multiplication is simple because the matrix A is sparse. So C is going to be simply 1, 0, 0, 0. Matrix C times A is going to be the first row of matrix A, which is 0, 1, 0, 0. You multiply this again with A, right? So CA squared is actually CA times A, meaning that this is a CA, so you kind of multiply this with A again. And in this case, it's going to pick up the first second row basically. So in this case, second row is minus K over M1 and all zeros. Now if we multiply this again with A, it's going to be all, so it's going to pick up the first row but multiplied with minus K over M1. So that's the observability matrix. Okay, and the next question is, what is the rank of this matrix? So I think, but by just looking at this, people can tell, because I mean, if you've read linear algebra, well, you see this is an upper triangular, right, matrix. So I mean, these two are 0, so you have 2 0 pivots. So I mean, I can directly say that the rank of A is 2, or rank of the rank of the observability matrix is 2, which is less than 4. So So the system is unobservable. And again, when we say unobservable, doesn't mean that the heaven is falling or the sky is falling. So I mean it means that a part of the system is unobservable. So there may still be a part which is observable. Okay, and comment here is that more specifically, it states x1, x2 are observable. Actually, for this you need to further reduce the observability matrix, but I'm just writing here as a comment that the first two states are observable while x3 and x4 are unobservable. Okay, and intuitively, if you want to understand this, you can look at the original dynamics. You will see that x4 is something like this. So x4 goes in and so there's no input affecting x4. X4 goes in and changes x3, but then x3 doesn't change anything else. So if you knew the output, which depends only on x1, and you know the input, you cannot say anything about x4. You cannot infer anything. So intuitively, you can also see that the state x4 is unobservable. The same thing for x3. x3 only depends on x4, right? So whatever x4 is, x3, the rate of change in x3 depends on that. So if you knew the output and you knew the input, there's hardly anything you can say about what the x3 and x4 will be at any point in time. So you can see that they are not observable, and the theory or the controllability or observability test has proved this fact. So just like the way we dealt with the system controllability, we can also try to bring systems in a form which is friendly for observer design. So that form we call as the observer canonical form.
Professor, could you do a Gaussian elimination as well to determine the observability?
Okay, so let's go back here and right. I mean, I could see it, but what you can do here is the first row stays as it is, right? Second row is 0, 1, 0, 0. And the third row, what I will do is I will multiply M1 over K1 times row 3 plus row 1. So the first element will become -1, and then if you add it to the first row, it's going to be all zeros. And the last one, I'm going to do M1 over K1 times row 4 plus row 2. So again, we have all zeros. So I can see that we only have 2 pivot elements and the others are 0. So I hope it is clear now.
Thank you.
Okay, so observer canonical form is in a similar idea. And the whole point is to make the design of observers more convenient. So formally, the observer canonical form of an LTI system is A0 or A observable. It's 0, 0, all zeros. Then we have minus A0, minus A1, all the way to minus A n minus 1. That's the last column. And then you have an identity here. So you will have 1, 1. All right, so basically this piece here is identity. This piece here is this piece here is coefficients of the denominator polynomial. So just a disclaimer here, again, this form of the observer canonical form is actually a convention that we use, but different books will use different conventions. And as I said in the beginning of the lecture, you can always exchange the rows and columns and it will be a new canonical form. So, but for this course, let's just restrict ourselves to this particular form. But in general, when you are reviewing the literature, you will find many other forms. Right? Every book author will use a form that is convenient to them. So the observer canonical form, the C matrix will be like this. You will always have a 1 at the end and the rest, everything is 0. Okay. And I'm going to say again that there exists a similarity transformation that will that can convert an observable system into its observer canonical form. Okay, and let's do a quick example. We'll see this transformation as well, but I think it's actually very simple if you just look at the characteristic polynomial and use this convention to write the canonical form directly. So for example, a system has the transfer function given by g of s, and it's going to be s plus 3 divided by s squared plus 3s plus 2. And the question is find the controller canonical and observer canonical form of the system. So I need volunteers now. I think this is a very direct kind of question. You don't even need to do anything. You can just do it by inspection. So what would be a controller canonical form for this system? So I can write to you because some people might have forgot the convention we use to write the denominator and numerator polynomial. So you can see that our A0 is 2 and A1 is 3 and A2 is 1. Right, so if you remember the convention, that's going to be A2s squared plus A1s plus A0. And for the denominator and for the numerator is similar. So we will have B1 is 1 and B0 is 3. Let's just say B0 is 3 and B1 is 1. Right, and if you want to be precise, I will say these are coefficients of denominator. Right, these are coefficients of numerator. So once we have these constants, I think the controller and observer canonical form are pretty straightforward. So let's just write them here so that people can refer to this example later. So the controller or controllable canonical form can be written as x dot is something x plus something u, and y is something x. Okay, and the observer canonical form can be written as x dot is something x plus something u, and the y is going to be something x, right? So I mean, it's simple. If I remember, the controller canonical form had A0 and A1 here. There was a 0 and then there's a 1 here. Right, so it's pretty simple. So let's so it's going to be 0 and 1, and maybe I should color this differently because this is already there, and only thing that changes is negative A0. It has to be appended with a negative sign, and A0 was 2, so it's negative 2 here and negative 3 here. The B was 0 and 1 here. And the C matrix is B0 and B1. So B0 was 3 and B1 is 1. I can also mark it here. This is negative A0. This is B0, this is B1. But for the observer, basically the rightmost column was actually negative A0 and negative A1. So in this case, we will have -2 here, -3 here, and then you had a 0 and a 1. Right? 0, 1 here. The B now had B0 and B1. So we will have a 3 and 1 here. And the C is now 0 and 1. Right? That's the convention we are following. So, I mean, somebody can prove that both of these systems are equivalent. And if you want to prove that, so let me ask you this question. If you want to prove that these two systems are the same, how would you prove it? I need volunteers here.
We form the GS for both system, and then we find out that they are both from one system.
What do we find for these systems?
Yes, a transfer function.
Yes, yes, transfer function. So, I mean, you have these systems, you have matrices, so you go to the transfer function, both of them will have same transfer function, right? So that tells you that in essence, these are the same. Okay, excellent. That's the right answer. Okay, so we've seen up till now, we've seen controllability of systems, we've seen observability of systems. So now we will see the relationship between controllability and observability properties. And interestingly, there is a very close relationship between them, and that's called a duality relationship. So they are kind of dual of each other. So duality of or between controllability and observability. So the duality property says that the pair AB is controllable if and only if the pair A transpose and B transpose is observable. It's a very useful property. And the same for the other way around. So the pair AC is observable if and only if the pair A transpose C transpose is controllable. So in some sense, this is intuitive because eventually you have to find the rank. So in one case, in the controllability case, you actually augment the vectors together to form that matrix. The observability matrix, you actually augment the rows. So in some sense, you just take the transpose and do a observability test instead of a controllability test. It's the same effect. But it's just an interesting duality relationship here, which is important to mention. So in other words, if I want to write it more clearly for you, it is saying that checking B, A, B, and so on for full rank. Is the same as checking B transpose, B transpose, A transpose, and so on for full rank. Okay, so that's the key idea, and it's clear that you transpose a matrix and you're doing the same thing. So instead of augmenting vectors together, you augment rows, but you kind of transpose the constituent matrices, and eventually you are finding the rank.
Sorry, Professor, it shouldn't be CAT, CTAT, and in the second one.
Are you saying the red pieces, this one?
Yes.
No, so we said, so if AB is controllable, that means you test this thing here. And A transpose, B transpose is observable. That means you test this,
Okay, thank you.
right? It's like a corresponding thing here. Okay, so following our previous line of action, when we were talking about controllable systems, I'm going to do the same thing here and say, what if the system is not observable, right? So luckily the sky does not fall, and we have ways to, again, go to a decomposed system. So, so intuitively from our previous experience, we would like to see that the system can be decomposed into an observable part. Right, so it's a observable part and an unobservable part. Using some sort of a similarity transform. So so the similarity transformation that will do the trick is X bar is equals to PX, where I should write it more highlighted. Where the matrix P is constructed as follows. So the matrix P will have several rows. So it will have P1, P2, all the way to PM, and then PM plus 1 all the way to PM. Okay, so like before, previously we were using columns, but here you will use basically M independent rows of the observability matrix. And And the remaining arbitrarily, these are arbitrarily linearly independent rows. Okay, so if you have this sort of a matrix P and you try to transform your system, then what will happen is that the system is going to decompose into an observable part and unobservable part. Right, so if you do this, let me write the resulting form. So resulting system using this transformation will have the following form. So it will be like x bar dot equals to a bar x bar plus b bar u, and the y will be c bar x bar, and you see this matrix A. So we really care about A and the C only here. So the A bar is going to be A bar observable, and then there's a 0 here. Then we will have A bar 2, 1, and A bar unobservable. Okay, and similarly, C is going to be C bar is C bar observable and a 0. So that's going to be a decomposition into an observable and unobservable parts. So let's do a quick example here to see how this can work. Just like the previous example which we did for controllability, we will have a system which is x1 dot x2 dot x3. This is going to be 0, 0, minus 6, 1, 0, minus 11, 0, 1, minus 6, x1, x2, x3. Plus something u, right? So it doesn't really matter. And yeah, let's say it doesn't matter. And the y is coming out to be 0, 1, minus 3x. Okay, so two questions. One is check the observability of the system. Okay, and the B is if unobservable, reduce it to an observable observable system. Right, that's typically what we want to do when this sort of a situation is encountered. So I think one thing is clear, that we first have to do the determination of observability. So pretty much that simple. So we construct a observability matrix of A and C, which is C, CA, CA squared. And in this case, the C is 0, 1 minus 3. If you do C times A, you're going to get a 1 here, minus 3 here, and a 7 here, and then minus 3, 7, and minus 15 here. So now we want to determine the rank. So, elimination is one way. So let's say we enter a let's first exchange the rows, because I think the row 1 and row 2. So that makes it a 1 minus 3, 7, 0, 1 minus 3, right? And then minus 3, 7, minus 15. Next step here is 1 over 3, row 3 plus row 1. So it's going to be 1 minus 3, 7, 0, 1 minus 3. And you've got a knockout here, 7 over 3. Okay, I need help here now.
Minus 2 over 3.
Minus 4 over 2?
Minus 2 over 3.
2 over 3. Okay, I hope you are right. And then the last one. 7 minus 5 is 2.
Yes.
Let's do it by hand. So I was saying 7 over 3 minus 3, right? So it's minus 2 over 3. Yeah, correct. And the next one is, 3 over 2, row 3 plus row 2. We have 1 minus 3, 7, 0, 1 minus 3, 0, 0, and 0, right? So we got 3, and 3 minus 3 is 0. So, okay, so at least one thing is clear. Since rank of observability matrix equals to 2, which is less than 3, so system is unobservable. Okay, that's the first part. And the second part is, can we reduce it to an observable system? So well, let's try to do that. So we need to do a transformation. And so to do an observable decomposition, we use the transformation P, and P is going to be composed of, remember, P1, P2, P3. So P1, P2 can come directly from the independent rows of the observability matrix. So independent rows are only 2. So I will look at these 2 here, 0, 1, minus 3, 1, minus 3, and 7. Right, so this is kind of 2 independent rows of the observability matrix A and C. And the next one I can pick arbitrarily. So I will just pick 0, 0, 1. It's a arbitrary row independent of other rows. So if I use this matrix P, then I can convert my system to the to a decomposed form, which will reveal the observable and unobservable parts. So the transformed system matrices will be the A bar is going to be P times A times P inverse, and the C bar will be C times P inverse. So if I do this, I will see A bar being this matrix P, right? And I use the old A matrix, which was 0, 0, minus 6, 1, 0, minus 11, 0, 1, minus 6. And finally a inverse. So inverse, I've already computed it. So you can verify it at your end. All right, so if I multiply these, what I get as A bar will be 0, 1, minus 2, minus 3, 0, 0, 1, 0 here, and a minus 3 here. All right, so this piece here is the observable subsystem, right? And this piece here was A bar 2, 1, and this piece here is the unobservable part. Now C bar is CP inverse, so it's 0, 1, minus 3, and P inverse was 3, 1, 2, 1, 0, 3. So if I multiply this, I will get a C bar, which is 1, 0, 0. So by comparing with the canonical form, basically this is the piece that is C bar observable, and this piece is unobservable. Okay, so observable system. So the observable system can be written as X observable dot it's A bar observable X bar observable plus B bar U, and the Y is going to be C bar observable X observable bar. Right, so I mean, if you do it, you will realize that you'll get two subsystems, right? So unobservable similarly in that style. Okay, so up till now we have seen both the concepts in detail: controllability, observability, how to decompose them into the separate parts. We saw the transformations. We saw a few examples here and there. The last thing today that we will talk about is a more general form of decomposition that takes care of all the observability, controllability properties, and that's called a Kalman decomposition. It's a most general decomposition of the LTI system. what does Kalman decomposition means? It's actually combining controllable and observable decomposition. Okay, so if you combine them, we can separate a partially controllable and observable system into completely controllable and observable systems. So it's a completely controllable, completely observable. So we can extract a subcomponent or a subsystem from the original system, which is both completely controllable and completely observable. So I'm not going to do a proof here, and it's rather not very productive to do it, but I will just mention really what the transformation is and what does it entail eventually. So if we had a x, which is the original state vector, we can actually transform it into x equals px, x bar equals to px. It will result in a vector of states which are x bar controllable, observable, x bar which is controllable but not observable, x bar which is not controllable but observable, and into some states which are neither controllable nor observable, right? So I will write it here. So this part is controllable and observable. So there exists a unique transformation P that can decompose the system into this form. And that's the most general form. So you can have a complete kind of a decomposition of your system. So these states are controllable but not observable. These are not controllable but observable. And these states are not controllable not observable. So if this was the original state vector, then using a transformation matrix P, this can happen. So we will briefly see what type of matrix can do it. I mean, obviously, it's hard to describe it fully, but I'm just going to write a brief description. So such a transformation matrix can be constructed as follows. So you have the matrix P, which is going to be, okay, I did something here. Okay, luckily. So P is written as P1, P2, P3, P4. So 4 subcomponents inverse, where the P1 so P1 belongs to the controllable observable subspace. P2 belongs to the CO bar. So now we're talking about subspaces and their basis functions. So P4 actually is from the uncontrollable, unobservable subspace, and P3 is whatever is left. So P3 along with P1, P2, P4 form a basis for the state space. So basically these individual P's are actually basis vectors. For the controllable and observable subspace, right? And CO bar, which is kind of C intersection O bar, it's the basis for controllable but unobservable subspace. So, I mean, obviously doing this is a arduous task, and we are not going to, obviously this only will be valid if there's a lot of states, right? So we are not going to do a practical example of this, but I'm just going to show you the format in which the result will be. So if you look at the result, you will have x dot co x bar dot co bar c bar o, and then x dot bar c bar o bar. This is going to be in a very interesting form. So you will have a bar controllable observable, we'll have a 0, a bar 2 1, a bar CO bar, right? So here we have zeros. Here we have a 1 3. We have a 0 here. A 2 3 bar. A 2 4 bar. A bar C bar O. We have a 0 here. We have a bar 4 3 and a bar C bar O bar. Right, so that Kalman decomposition is going to generate the matrix A bar in this format, and you can pick the subsystems which are partially controllable, partially observable, or both, or whatever whichever subsystem you want. So this is the state vector. So this is kind of the most general decomposition, and the B is also in a specific form. So you will have BU, but the first one is B bar CO, and then B bar CO bar, and then that's it. You have the zeros in the remaining elements, and output Y is something like this: C bar CO. And then we have a 0 here, and then C bar O, and then 0 X bar plus du. So I mean, if in a diagram you want to represent all of this information, you can say that the system decomposition looks like this. There is a input U, which goes into a controllable and observable system, and that's generates an output Y. Now there's a piece that is controllable but not observable, right? So basically that takes the input and in the feedback loop, basically there's a piece which is not controllable but observable, and there's a piece which is neither controllable not observable. Right, so we have these two pieces, and obviously they do get the outputs because oh, actually not the last one, right? So so this is the type of system that you're looking at. So the one which is observable, you can use that to estimate the state and then do a feedback controller, but the other pieces are the other pieces are not into your control. So when we look at these type of decompositions, we are saying that, you know, this is the piece which is the most interesting, but hopefully this is stable, right? Which is uncontrollable, right? So this is stable because it is uncontrollable. And hopefully, you know, this piece also is stable.
Is it uncontrollable or unobservable because of a?
Well, observability doesn't matter because it's a C bar. So if these two are stable, then, you know, you can still use a feedback controller, right?
Okay.
Otherwise, there's nothing you can do because these states will just blow up. They will go to infinity. So if that's the case, that your uncontrollable modes or uncontrollable subsystems are stable, then even if this is not stable, you can do something. You can use a KX, right? And you design a K that makes it stable. Right. But these pieces, the other pieces, you have no control over them. So changing the input is not going to change anything. Oh, I mean, it's so unobservability is here. Oh, I think you were right. I think this is unobservable, right? So even if it is, I mean, it's unobservable, it should be stable. So hopefully we don't have issues. Right? And here it is uncontrollable. And basically, you know, this is the system of interest. And from the next lecture, we are going to focus on this piece and just making sure that other pieces are not problematic. So so in other words, when I say, you know, the other pieces are stable, it means that their eigenvalues are within the left half plane, or they are within the unit circle. So just writing one statement and we are done with our lecture. So in other words, the eigenvalues of A C O bar, A C bar O, and A C bar O bar are in the left half plane or within the unit circle. So this piece only when for continuous time systems and this for the discrete time systems. All right, so any questions from today's lecture or anything else?
I have a question. It's more general. You know, for both controllability and observability, we
Yes.
use the controllability and observability matrices respectively. But for controllable decomposition and observable decomposition, you know, we use the similarity transformation, which is extracted from those matrices. But I don't know whether just two columns or two rows are every time are independent columns and rows, and the third column is arbitrary vector, or we should find that which rows is independent or which column is independent.
Okay, so that's a good question, but the thing is, if we are looking at a 3x3 matrix, and for example, let me go to the case here. So we saw the observability matrix, and so it comes out to be a 3x3 matrix. So 3x3 is a very simple case of a linear independence, right? If you have two vectors, they are most likely independent unless they are the same, right? So two vector case is very simple, right? So unless they are in the same direction, they are always independent. But when there's three vectors, then any two of them can be independent, right? Only one can be dependent, meaning you know, if this is the case, then you can pick any two, like this, or you know, this and this, or this and this. Do you see my point?
Yes.
So I mean, in this case, any two can be picked. So that's the reason why it really doesn't matter. But in general, if there's a large matrix and you have you know, a lot of states, then the question is you have to figure out which state is observable or which state is controllable or not. So I mean, I give you an example here. When I exchange the rows, basically, this is something which will create a confusion later, right? Because if I keep exchanging rows, then that's going to change the order of the states. So maybe here, x1 became x2 and x2 became x1. So that's something you should not do if you have a large matrix. I mean, you can preserve the order and then you will know which two are really independent, or which three, or which four. Do you see my point, or you still have?
Yes, no, thank you.
Yeah, I mean, in this case, I was being a little bit sloppy by just, exchanging rows and because it doesn't matter, x1 and x2 are both independent. So I changed the rows, the order of the rows, and I said the rank is 2. But there are more details as the state space becomes larger, then more stronger linear algebra knowledge needs to be in place.
Is there any function in MATLAB that we find which rows are independent or not?
I think there should be. I'm not aware of it. Actually, if you find the eigenvalues, I think that's going to tell you something about it. So there's a, I mean, if you have a matrix, then, right, let's say that the eigenvalue is 2 here and 0 here and -1 here. So I know that the first vector and third vector are independent, right?
Sure, yes.
One of the eigenvalues is 0 because obviously it's not invertible. So, I mean, if all the 3 eigenvalues are non-zero, then all 3 are independent. So MATLAB will give you an ordered eigenvalue, right? So maybe the first one is 0, then -1, -3. So you can figure it out.
Thank you.
Sure. Any other question? Okay, so up till now we've seen the first quiz and we've seen the first homework, and this week is going to be quiz 2, right? Or have you had the, yeah, so quiz 2 is this week. You already have homework 2, right? Okay, so quiz 2 will be out this week. And I want to mention one important thing about the quizzes. I mean, it should be very obvious. So no collaboration is allowed, right? So in the previous quiz, I feel like people have not been completely, or let's say, I don't think everybody has done his own work. So I've started doing a random oral quiz, right? So I've selected a few people, and just like in the airport, you can be scanned randomly. Here I am setting up random oral quiz to ensure that there is, to minimize kind of the unfair means. Right? So if that happens, basically it means that I'll ask you a few questions, and based on that I will adjust your score, right? So try not to copy from here and there, because otherwise you might get into one of these quizzes and then we will discard your original score and readjust it based on your oral performance. Right? And it's a graduate course. I expect that everybody acts professionally, and eventually, grades will not matter. So as long as you do a good job in the course, I think you should get a decent grade. So don't try to use the undergraduate type of tricks here. Okay, so that's all. Is there anything else you want to talk about before we end the lecture?
So the quiz will cover today's material and last week's.
Yeah, roughly. It doesn't go beyond the two lectures. And the lectures are in front of you. You don't have to, you can always consult it during the quiz. So, and there's enough time. I think in an hour you can go back to the notes and do a quick review if required, but don't collaborate with other people and do not use unfair means. So every time we will randomly pool few applicants and few students and do a oral quiz. Anything else? Okay, if not, then let's meet next week.
Thank you for your time.
Yeah, all right. Thank you, everybody, and have a great
Thank
week.
you.
Thank you, Professor.
Bye.
Thank you.